Hello everyone, in this video you'll be learning about multimodal sentiment analysis. Firstly, I'm going to talk about the definitions and the types of multimodal learning and see some challenges and issues and the recent methods. And finally, I'll finish off by giving some Pytorch implementation tutorial. And what is modality? Humans communicate with text, voice, and facial expressions. Modality is the adopted mode or media for communication. For example, if someone understands one's emotion by facial expressions, then the modality is vision. And if he understands the feeling of another from letter, then the chosen modality is text. In the early days, modal predictions happened in the same modalities. For example, text to sentiment classification used only text, and for audio to sentiment classification, only audio modality is used. And these days, multimodal learning is a popular trend that combines different modalities for the final task. And there are two fusion methods. The first one is early fusion, and the second one is late fusion. In the early fusion, it uses delicate attention mechanisms for cross-modal fusion, and there are two examples, which are memory fusion network and cross-modal transformers. And late fusion for inter-modal fusion is performed after having learned intramodal representations. And the examples are tensor fusion network and the low-rank multimodal fusion method. And there are 5 core challenges for multimodal learning, which are alignment, translation, representation, fusion, and coloring. Among them, today I'm going to discuss about representation learning. So, what is modality gap? Modality gap is caused by the discrepancy between heterogeneous modalities at an utterance containing stylistic information sensitive to a speaker. For example, the affective polarity can be biased due to the peculiar or sarcastic expressions of a speaker. Although these speaker-sensitive information have been considered as noise, they can provide complementary information which may be lost while projecting their features to a common space. So, to address these issues, recently MISA projects each modality into 2 spaces to preserve both consistency and complementary information. Shared encoder projects each modality to a common space, and private encoders project each modality to their respective spaces to extract their unique features. That is, unique representations of each modality are learned by the corresponding private encoders. So you can see the overview of MISA architecture, and for an utterance, there are 3 modalities, which are visual, audio, and language, projected to a common space, each modality represented as a blue triangle, and each modality also is projected to their respective private spaces and giving 6 representations per fusion and for final prediction. So I'm going to give Pytorch implementation tutorial, and I note that the code is adapted from MISA, and if you want complete code, you can email me to the following address. So for the dataset, I used Rabodesk, and the link is as follows. It contains 24 actors vocalizing their emotions with the following 8 emotions, which are neutral, calm, happy, sad, angry, fearful, disgust, and surprised. And the left video demonstrates some angry emotion.
Dogs are sitting by the door!
So in this project, only speech videos from 24 actors are considered. And for pre-processing, given a video file, I have saved the audio features and facial expressions into a pickle file with the following feature extraction methods. So for audio, analog digital analog signal is transferred to digital signal, and this digital signal is converted to um, using short time Fourier transform, and then this is also transferred to MFCC, short for mel frequency cepstral coefficient. And to extract visual information, facial actions units, which are movements of facial muscles while a person is speaking, are extracted as defined in FACS, facial action coding system, using OpenFace. So if you need more details, you can check the reference links. And the dataset is split as follows for experiments. Out of total 1,440 features, consisting of both audio and visual features, 180 are used for test, 240 are used for validation, and the rest 1020 are used for training. The dataset have been shuffled before splitting randomly, and then let's see the code for shared encoder. You can see that the shared encoder layer projects, and then there is a sigmoid for activation function, and utterance V and utterance A in figure 2, they each represent their the visual and the audio modalities, and you can see that only the same encoder, shared encoder, is used to project their representations. And on the other hand, if you see private encoders, there are private encoders. The encoders for visual information and the encoder for audio information is different. And for if you see in figure 5, then you call private V, which is private encoder for visual information, and you call private A for audio information. So you can see that these two encoders are different to project their unique spaces. And as can be seen in figure 5, different encoders are used, which are self-dot utterance private V for visual information utterance V, and self-dot utterance private A for audio information utterance A. So for fusion, layer is defined as in figure 6, and the four representations projected in the earlier slides, the private audio features, private visual features, shared audio features, shared visual features, are going to be passed to above fusion layers shown in figure 6. So the inter-modal fusion happens as in figure 7. Each of the four representation can be concatenated using torch.cat function as in figure 5. So if you see the torch.cat, the HO, which corresponds to the private visual representation, and H1 corresponds to self-dot utterance private A, which is the private space for audio, and self-dot utterance shared V, self-dot utterance shared A. If you remember that they use the same shared encoder to project their spaces. So the experimental results shows that using private encoders, um, in addition to the shared encoder, it shows 1.1% increase in the accuracy compared to using only shared encoder. So, however, the results may change due to the stochastic nature of the neural networks. And I also note that it is not stable because other regularization methods are omitted for simplicity. And here are references, and I want to finish off here for today's presentation. So thank you for listening. Bye.